Okay, so today we're doing periodicity. Our syllabus outcome is to demonstrate, explain, and predict the relationships and the observable trends in the physical and chemical properties of elements in periods and groups in the periodic table, including but not limited to state of matter at room temperature, electronic configurations and atomic radii, first ionization energy and electronegativity. There's also one there that says reactivity with water. Now, the reactivity with water we'll actually cover in module 3 because we have to do it again then. So we'll cover the periodicity of reactivity with water in module 3, but the rest we're doing today. So just make sure you have a go at the revision questions at the top of page 77. If you haven't, pause this video and have a go at them. If you have, let's go on to the answers. So atoms contain what? Well, they contain protons, neutrons, and electrons. The atomic number is equal to the number of protons. Neutral elements have the same number of protons and electrons, as opposed to ions, which have different numbers of protons and electrons. Electrons exist in shells within atoms, and the outermost shell of the atom is called the valence shell. Okay, so you might remember all of that stuff from structure of the atom. So that actually helps us a bit with today, because a lot of the trends on the periodic table actually relate to valence shells and the actual shells as well, or like the total number of shells. So, periodicity. In the context of chemistry in the periodic table, periodicity refers to trends or recurring variations in element properties with increasing atomic number. Periodicity is caused by regular and predictable variations in element atomic structure. Now, basically, there's predictable ways that everything's put together. And we're going to have a look at some of the ways that, or some of the trends in the periodic table. The first trend we're going to look at is atomic radius. So firstly, how do we measure the radius of an atom that has no definitive edge? Okay, so while we do say things are in shells, we do have that. It is kind of fuzzy. Okay, it's not a hard shell. So how do we measure that? Well, we just measure the distance between two atoms in a solid. Okay, so we get basically the distance between the center of two atoms is 2 times the radius. So we take half that value and that gives us our radius. Now, the actual atomic radius, it's influenced by 3 factors. So the shell level, so whether it's 1n, 2n, 3n, etc. Basically, higher shells are further away from the atom. The charge on the nucleus, as we get into larger and larger atoms, there's more charge in the center, pulling the electrons in. And something we call shielding effect, which is repulsion from other electrons. So electrons don't like to be too close. So as that charge pulls them in, they do start to push on each other. So it does actually affect the actual size of the atom. Now, as for the trend, so the group trend, so remember groups are our columns. As we go down a period, the atom has one more electron shell, so the atom gets bigger. So if we have a look at group 1, so hydrogen, lithium, sodium, potassium, rubidium, it would continue for cesium and francium as well. We can see that as we add a shell, the atom gets bigger. So hydrogen is the smallest, lithium is the next one, then sodium, then potassium. And it's just as we go down a level, we add an extra shell, it gets bigger. Now, as you go across a period, so these are the rows that we're talking about, the radius gets smaller. So electrons are in the same energy level, but there's more charge in the nucleus. So we actually have them pulling in. Okay. So the outermost electrons end up being closer. So if we have a look at the, I think it's the third period. So sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Now this isn't exactly to scale, but it gives you a sense of what happens. So sodium, out of all of them, even though it has the least amount of protons and neutrons and electrons, it's actually the biggest out of that period because we're only adding electrons into the valence shell. So the valence shell is not getting bigger, it's actually getting smaller because as more electrons are added, it's getting pulled in. Those electrostatic effects are pulling it in tighter. Here's a good example. This is just a graph of the atomic radius in nanometers compared to the atomic number. Okay, so we can see that from lithium, the radius dramatically drops and then it kind of decreases nonlinear. But as soon as we hit neon, which is the end of the second period, it jumps up to sodium. So it's a big jump. Then it gets smaller and smaller and smaller and smaller again. Argon's the end of the third period, so it jumps up and then it starts going down. But then we have this weird kind of bump. Okay, so this is the transition metals. They're kind of funny, basically. And then it goes to krypton. Krypton jumps back up, and it follows that same pattern with that bump towards the end of the transition metals. And I reckon the next one, it's not actually shown, but it'd be very much the same. Okay, sort of thing. So that's atomic radius. Ionization energy. So ionization energy is the amount of energy required to completely remove a mole of electrons from a mole of gaseous atoms. Now, I know you guys haven't learned about what the mole is, but it's basically a certain, like a set amount. It's the actual number is 6.022 by 10 to the 23. So ionization energy is the amount of energy required to remove 6.022 by 10 to the 23 electrons from 6.022 by 10 to the 23 molecules of gaseous atoms. So removing the electron makes a +1 ion, and the energy required to remove 1 mole of the first electron is called the first ionization energy. Okay, ionization energy as a whole encapsulates first, second, third. It's different for each atom, I think ionization energy goes to where it's stable. First ionization energy, which is the one that we compare, is removing just 1 electron. Okay. We have second ionization energy, so that's removing a second electron. And it's always greater than the first ionization energy. So it's usually easier to pop off 1 electron than it is to pop off 2. Third ionization energy is the energy required to remove the third electron. And it's actually greater than the first or second ionization energies. Okay, so it's the most energetic. So it's more energetic than the first or the second. So if we go and have a look, so we can have a look at the amount of energy. So these energies are listed in kilojoules per mole. Now again, it's just per set amount. Okay. Now we can see that the first column, apart from hydrogen, they're actually pretty low numbers. Okay, so about 500. But they decrease as we go down period, so they increase as they go up. So down a group. As we go across the period, the ionization increases, so it takes a lot more energy to take an electron from things like fluorine, helium, neon, than it does from cesium. Okay, so basically ionization energy increases up a group and towards the right, so in this direction. So that's ionization energy. Next one's electronegativity. Now, electronegativity, it's the tendency for an atom to attract electrons to itself when it's chemically combined with another element. High electronegativity means it pulls the electron towards it, so they have a higher electron affinity. Atoms with low electronegativity are usually referred to as electropositive atoms. And atoms with large negative electron affinity have larger electronegativity. So this is our electronegativity graph, okay, or table, sorry. So we can see that as we go down down a group, sorry, the electronegativity decreases. So smallest is francium at 0.7, and as we go up towards fluorine, we can see that they're increasing. Now we can see on the very last column. Helium, neon, argon, radon, they don't have numbers. Now that's a thing to do with the octet rule. They don't really like to attract them because they're already full. Krypton and xenon do have some, but again, we kind of ignore them because they're noble gases. So electronegativity group trend. So the further down a group, the farther the electron is away and the more electrons an atom has. So it's more willing to share them, basically. Lower electronegativity at the bottom of the group. Now for the period trend, metals are at the left of the table. They let their electrons go quite easily. Okay, so they're more electropositive, and they have low electronegativity. Now, at the right side of the periodic table, more towards non-metals, they want more electrons. Generally, they're more stable um, when they have more electrons, close to that octet rule, and they try to take them away from others. So they basically have a high electronegativity. State of matter is another one. So this one, I'm not letting you. I don't. Sorry, I'm not getting you to write anything about this, but just have a look at it. The basic trend is that most things are solid at room temperature. So remember, our room temperature is typically stated at either 20 or 25 degrees. This one's at 20, but at 25, it's still the same. A lot of them are gas. Some of them are gases. So hydrogen, helium, a couple of the halogens, as well as nitrogen, oxygen, and the noble gases. So they're all gas at room temperature. And there's only a few that actually exist as liquids. So there's bromine and mercury, the most common ones, and then there's CN down the bottom. So I don't think CN, I think that's more of a predicted state of matter because I don't think they've actually produced enough of it to measure, its melting and boiling point or anything like that. But I think that's just based on quantum mechanical predictions. But yeah, so basically the basic trend is to the left it's solid, to the right it's gas, and there's a couple of liquids that just exist. There's some that are very close to being liquid at room temperature. They're cesium and gallium as well. I think some of their melting points are between 30 and 40 degrees, so it's pretty low. So let's have a look at the summary for today. So atomic radius, as we go across a period, it decreases. As we go down a group, it increases. Ionization energy, it increases across a period and decreases down a group. Electronegativity increases across periods, decreases down the groups, and state of matter, across the period it becomes less metallic, so more likely to be gas. As we go down, it becomes more metallic, so more likely to be solid. And so that's a handy little chart. So just below, just in the summary section, I've given you that blank periodic table, so just copy that onto it. It's just an easier way to help you remember the general trends. Okay, and that's all for today.